Okay, so binomial distribution is basically the sum, the function of the random variables, and our random variables are Bernoulli random variable, and their sum is called this binomial distribution. And here we have another assumption that each Bernoulli random variable is statistically independent of each other. Okay, so so in the previous example we had these five Bernoulli random variable, and then we considered their sum, right? So in this case, G is defined in this form. Okay, then and we considered all the possible values which will form the event space of our function G, which is a binomial random variable. So it ranges from 0 to 5 when we have a five independent Bernoulli distribution. And then we can compute the mean and the variance. So since we learned about the new distribution, we can think about the mean and the variance of it. So in the previous case, let's call that binomial distribution or binomial random variable as B, which is, let's see, G of x1, x2, x5. Okay, so this is x1, x2, x5. And then we can consider the mean or expectation. So this new random variable, or the expectation of the functions of x1 through x5, is represented in this form. And then since they are sum of those multiple random variables, whether they are statistically independent or not, we can always rewrite this into this form. So we can basically distribute this expectation operator in this form, right? So again, this is always true, even if they are statistically dependent, right? And then we know that this guy is, for example, P. What was x1? It had a 0 and 1, and then the probability was, for example, 30%, 70%. And so this was called P. And so in this case, how can we compute the expectation? We consider all the possible values and then multiply it with each of these associated weight value or probability value. And then since this guy is 0, we can ignore that. And then the resulting value will be just P. So basically the expectation of each Bernoulli random variable is just the probability of being 1. So in this case, since we have 5 different random variable, is 5P. Okay? So in general, if we call 5 instead of 5, we call that number as n. Then this value becomes n times p. So that is our expectation value. Then we can also compute the variance in this form. Minus mu of gx1 through x5 and squared, and then we have some probabilities, right? At this in here, this should be f of an x1 through x5. So you guys know the meaning of this function f. So that is the joint distribution. Joint probability distribution. of original random variable x1 through x5. Okay, so in this case, instead of, yeah, so it's not exact. So in this case, x1 through x5, or in this exact in this specific case, we are considering the discrete random variable. So this integral sign is no longer true. So it should be change it into the summation. x1 through x5, and then this part coming here times this guy, right? But we will utilize another formula that we learned, which is this guy. So in this case, the variance can be also defined in this form: g of x1 through x5 squared, the expectation of the squared random variable, or this function, minus g of x5, and then squared. Okay. So this one allows us to easily compute this guy. So in this case, so let's first look at this, because we obtained this, right? So this is np, and then squared. We have to take the square of it, and then what will be this guy? How can we compute this guy? So in order to compute this, we can rewrite this by just plugging in this definition: x1, x5 squared, right? So we want to compute the expectation of this. Then it becomes the same as x1 squared plus ex2 squared and ex5 squared. Okay, and why should that be true? So originally this guy should be written in this form. So we can just simply take the square of it, which is x1 squared, x2 squared, x5 squared, but we also have additional terms, which is 2 x1 x2, 2x1 x3, and so on. So we have all these cross terms, right? And then we can distribute this expectation operator into each of these terms, whether they are square term of self or these cross terms, right? But for each of these cross terms, in this case, we can rewrite this into x1, x2. Oh, yeah, with the 2, right? Why is it true? Why is it true? Okay. Why is it true? Yeah. Yeah, so one student answered that because they are statistically independent, Okay. Or this one was called as another name, or we called it in a different way. What was it? So let's just simply remove this. So in this case, that should be the same as this. So it was called uncorrelated as well, right? So this was called uncorrelated. So what was the uncorrelated? I mean the meaning of the uncorrelatedness? The covariance between x comma x1 and x2. So this guy should be 0. So this was uncorrelatedness. And then from here we derived this guy is equivalent to this guy. Okay. Marginal, conditional. Okay, it was chapter 4. Okay. So here in this case, the covariance being 0 means that they are uncorrelated, and then they are automatically statistically independent, right? And then this uncorrelatedness, okay, so we didn't, we learned this theorem in this way. So yeah, it's an easier situation. So we start with this independence. So if they are independent, then the product, I mean the expectation of these multiplication of these two can be decomposed into the expectation of each variable and then multiplying them later, right? So just to recall how we understood this or how we were able to prove this was that, so we start with this and then joint probability, and this joint probability is written in this form, right? And then due to the statistical independence, we can change this guy into this form, right? Then these two can be plugged in here, and then this guy and these two guys are belonging to each of these integral signs. So each of these integral becomes the expectation of individual or single variable. Okay, so in this case, we started from the statistical independence. So this guy will become the same as the multiplication of the expectation of the single variables. Then these guys will be from here. What is this value? This will become p, right? So it should be p squared. Then what about the first part? So e of x1 squared, what is the expectation of this? 네? 뭐라고요? 다시 한번. So we start with the 0, 1 as a unique variable, unique values for x, and we change it to x squared, and then it becomes 0 and 1, and then the probability will be 1 minus p and p. And then what is the expectation of this x squared? It's just, it's just a p. Is it right? These are the values. They look the same, but these are squared values coming from 0 and 1 each. And then we associate their probability values and then take the weighted average. And then it will be just the same as an expectation of just an x itself. Okay? So here, so we know each of these have the same expectation value, and here we have 5p. So we have 5p, and then plus, here we have p squared, and then how many terms of this? How many terms do we have? So n, so 5c2, or it is change it as np, and then it is nc2, then p squared minus, we had np squared, right? Then we change it 5 to n, so np plus, what is this guy? N times n minus 1 over 2 times p squared minus np squared. Okay? And then after we derive it, it will be equal to this. Somewhere I made a mistake, I guess. Where is it? Ah, okay. Here we should have n squared p squared, right? I made another mistake here. So we originally had these two, right? So this entire number should be multiplied by 2. So we should have 2 here. Okay? So that way n squared, p squared will be cancelled out here. Okay? And in that case, np and np squared will be the remaining terms, and then after we factor them out, we will obtain this. So this is a binomial distribution. Okay. And then the next distribution is called hypergeometric distribution. Yeah, in this case of an hypergeometric distribution, so the story is as follows. So we started with the Bernoulli random variable, and then we considered the summation of multiple Bernoulli random variable. Okay, so in total we have, for example, n bowls in our basket, and then we pick up some number of bowls from this basket. Okay, and then the number of bowls that we pick up from our jar or our basket can be viewed as binomial distribution. So it's something like this. So we have x1, x2. For example, we have 5 bowls here in our basket. And then we decide for each bowl we pick up, or we just leave it in the basket. Okay, and then the total number of bowls, okay, can be viewed as the binomial random variable. Okay, so observing 3 bowls out of 5, what is the probability value? And that probability value is what this binomial random variable is telling us. And each bowl has a given probability value. So whether this guy will be picked up or not, that situation has its own kind of probability. So each bowl has a 70% of being picked up, okay, and then 30% of being remaining in the basket. Okay. So in this case, we can consider this situation as this. So we only have just a single bowl. Then we repeat the process of picking up or not. Okay, and then after we do this one time, and then we put this bowl into the basket again. So that is called this sampling with replacement. Okay, but there can be another situation, which is a sampling without replacement. So in this case, a little bit more familiar situation is that we have 3 circles in the bowl, in the basket, and then maybe 2 triangles and 4 stars. So here okay, let me just simplify the situation so that we have only 2 different kinds of bowls. So one is circle, and then the other is a star. And so here in this case, at first the average probability of picking up this star is 4/7. And then we pick up 5 bowls, okay, and 5 bowls, and then after picking up 1 bowl at a time, after we check whether that bowl is a circle or just a star, then there are 2 different situations. One is that we put our bowl back into the basket, or we can just leave it aside for those bowls that was picked up. So suppose we first picked up this bowl. So this was our first bowl, okay, and then we checked that was the circle, and then if we put it back in this basket, and then the situation will remain the same, right? But if we do not put this guy back in this basket, and then the overall probability will change, right? So in this case, so picking up the star, the probability of picking up the star will be 4/7, but in the next sampling step, this probability will remain the same if we put this ball into the basket bag, right? So we consider these two different situations. And then the binomial distribution can be viewed as this type of process. So here we have, this, let's use this triangle, and then the rectangle. So here we have a probability of picking up this rectangle is 0.7. And then suppose we pick up 5 balls in a row, 1 ball at a time. But at this process, we put our ball into the basket bag. In this case, it's exactly the same situation as the binomial random variable case. So in this case, for example, what will be the probability of picking out of 5 balls that we pick up? What is the probability of picking 2 triangle and 3 rectangle? It will be 0.7 to the power of 3, and then 0.3 to the power of 2, right? And then we have to multiply it, okay? And then this guy will have a different orders, and that different order will be NC or 5C 3, because we have 5 slots, and then at the first slot we put our ball that we first pick up into this slot. Okay, so in this case the order could be this, or it could be this, right? So all the different order will have this many number. So that way we multiply these are different cases, the number of different cases. So that was the binomial distribution situation. But what about not replacing or not putting back the ball that we picked up into the bag? So in this situation, let's think about the probability of observing those outcomes. So this is one event or one event instance out of our event space. So in this case, the probability will be (3 over 10), which is a 0.3. And then the next one, what will be the next probability of picking up this square? It will be 7 over 9, because we reduce the total number of elements in our basket, right? Then picking up the triangle will be 2 over 8, because one was already picked up in the first place, and then another rectangle was picked up, and then the remaining total entry is 8, and then the remaining triangle will be just 2. Okay, so this is called sampling without replacement. So replacement means we put the sampled one into the basket so that the probability doesn't change. So in this situation, we can also consider similar kind of a random variable to binomial distribution. So what was the value of the binomial random variable? So in this case, the binomial random variable is basically out of 5 trials, the probability of picking up maybe 2 rectangles. Okay, so basically the probability of the number of rectangles being 2 out of 5 trials. So that was the binomial distribution, or the meaning of binomial random variable. So we can consider similar random variable in this situation where we do not replace. So out of 5 trials, our new random variable will still represent or still mean the number of rectangles that we observe out of 5 samples that we picked up. So in this case, the total probability of this count will be different. And that probability can be computed in this form. Because we are not replacing our bowl into the basket, we basically, so the entire number of different cases will be, so we have 10 bowls here, so all the possible cases will be this number or this number. Why is that? We are because we are sampling or picking up 5 bowls out of 10, right? Out of these numbers, we have to, so let's fix this value as 2, for example. In this case, so we have, out of 5, we have to pick up 2 rectangles. And then the total rectangle was, the number of total rectangle was 7. And then we have to pick up 3 triangles out of the total number of triangles, which are also 3. Okay, so these are the number of different possible cases of satisfying this criteria or this situation, where the number of rectangles are 2, and then out of 5 samples. Okay, and then in the denominator, we see this the total number of different cases of sampling just to 5 bowls out of 10 bowls. Okay, so this is called geometric this is called this hypergeometric distribution. Okay, so far we learned about the 2 different random variable, which seems to be a little bit tricky. But we basically started with the Bernoulli random variable, and then we extended it to binomial random variable, right? And then also, as a slightly different situation, we learned about this hypergeometric random variable. Okay, so in this case, the random variable value can have its own unique values. Okay, so and then also its own associated probability values. So it's just another random variable. And so let's call this random variable as C, for example. And then let's consider the all the possible unique values of this random variable. So in this case, the meaning of it is the count or the number of rectangles that we see out of 5 samples. And then in the case of binomial random variable, it was ranging from 0 to 5. But in this hypergeometric random variable, this range becomes smaller because we cannot observe 0 values in this specific case. Why is that? So in other words, can we observe the count of rectangles as 0 out of 5 samples that we pick up from this basket? Oh, yeah, it is possible, right? We can pick up these 5, right? So 0 is definitely possible. And then 1, 2, 3, 4, 5 are all possible, right? So in this case, the range or the unique possible values for this random variable will be the same as the binomial distribution. But what about this? We slightly change the random variable in a way that this random variable means the number of triangles out of 5 trials. No. Yeah, so I was a little confused. So in this case, this 0, is this 0 possible? So again, the number of rectangles being 0, is this case possible? The answer is no, because if the number of rectangles are 0, then the number of triangles should be 5, because we are always obtaining the 5 samples. Okay? Because we do not allow the replacement. Once we pick up 3 triangles, and then the only possible types will be just rectangles. So the remaining 2 will have to be just rectangles. Okay? So we have 5 trials, and then suppose we picked up 3 triangles, and then there is no other triangles anymore, and so we have to pick up those rectangles for the remaining 2 trials or 2 samples. So in this case, the number of the squares, the minimum number will be starting with 2. Okay, so 2 to 5. So for those 4 different values will form our event space. Then each of these probability value is computed in similarly to this equation. Okay. Any questions? Okay, so in this hypergeometric distribution, they have their own mean and the variance value. Okay, and then in these cases, we cannot easily prove these mean and the variance value, but we can just understand this as a kind of similar values to the binomial case. So in this case, if the total number of balls in our basket is really large, then whether we replace or not, it will not impact the result much. So in these cases, the binomial distribution and hypergeometric distribution will always, they're almost the same. Okay, so they are just a slightly different. So it's a matter of a replacement, and so that makes this NP of a binomial distribution into this value, and NPQ into this a little bit complicated form, but their meanings are almost similar. Okay, and then we will learn about it in the next week. Okay, and then that's it for today. And sorry for being late today. Then also again the homework is out, and then it's due next Wednesday, okay, before the class. And also, as you guys know, the next Monday is a holiday, so we won't have a class. Okay, So see you next Wednesday.